Hello! Today we are going to be learning about Bohr-Rutherford diagrams. Bohr-Rutherford diagrams. Yay! So the reason we're learning about Bohr-Rutherford diagrams, this is a model of an atom that's really helpful in arranging electrons in our atom, which is going to be useful when we just start talking about the way that atoms bond together to create molecules. But first, we need to learn what this is going to look like in our simplified conceptual model. So in order to do this, you're going to need a periodic table. And we're going to be using carbon as an example. And if you look at your periodic table, you're going to look for the letter C, which is for carbon. And when you find C, you're going to find a couple of things along with it. You're going to find the name carbon, usually below it. You're going to find the number 6, usually in the top left corner. And depending on the periodic table, you're going to find another number, which for carbon is going to be the number 12. And this is all going to be in a box looking something like this. Now, each of these numbers has a specific use in our Bohr-Rutherford diagram. Now, just first things first, this C is the atomic symbol for carbon. So whenever you see C in a molecule or a chemical formula, you know that it is carbon. And you can double check for other elements because the name is always going to be underneath it on the table. The number 6 here is an important number because this is the atomic number. And carbon is the only element with the number 6 as its atomic number. And the atomic number is important because the atomic number is equal to the number of protons. The number of protons. So that means that every atom with 6 protons in its nucleus is going to be an atom of carbon. So the thing that gives an element its physical characteristics and determines what element it is the number of protons. Now, interestingly, in our idealized Bohr-Rutherford diagrams, all of our atoms are going to be neutrally charged. So the number of negative charges are going to be equal to the number of positive charges. Now, protons have a positive charge of 1. And it just so happens that the number of electrons is going to be equal to the number of protons in our idealized model, because electrons have a charge of -1. So in a neutral atom, the number of protons equals the number of electrons. Now, in order to draw our Bohr-Rutherford diagram, there's one more thing that we need to know, and that is the number of neutrons. Remember, we have protons, electrons, and neutrons in our atom. And the way that we calculate the number of neutrons is by looking at this number here, which is our atomic weight. Atomic weight. And the atomic weight equals the atomic number plus the number of neutrons. So in order to find the number of neutrons, we take the atomic weight and we subtract the atomic number. So for our carbon molecule, just write charbon there, for our carbon molecule, the number of protons, which we say is P negative, is going to be, or P positive, sorry, is going to be 6. The number of neutrons, which we call N naught, 0 means no charge. Number of neutrons is going to be atomic weight 12 minus the atomic number 6 equals 6. And the number of electrons, E negative, E for electron, negative for negative, is going to be the same as our number of protons, which is 6. I'm just going to draw a little arrow here. Actually, let's make that a different color. Just going to draw a little arrow here indicating that they are one and the same. Oh boy. I'm going to make it green, because why not? These guys are the same in a neutral atom. Okay. Now, let's get to our Bohr-Rutherford diagram. So step one, draw the nucleus. Okay, and the way that we're going to do that is we're going to first draw a circle like this. Maybe let's make it a little bigger. First, we're going to draw a circle that looks something like this. And since we know that protons and neutrons live in the nucleus, we're going to draw a P positive and an N naught here. So protons and neutrons live in the nucleus. So going back up to our reference here, we know that there's 6 protons and 6 neutrons. So for our nucleus, we're going to say P positive equals 6, N naught equals 6. So there you go. That's your nucleus. Now step 2, we're going to draw our electrons. So remember, in a neutral atom, the number of electrons equals the number of protons. So there's going to be 6 electrons. 6 electrons, but they don't live in the nucleus. Electrons live in electron shells that, I'm going to say orbit, but in quotes. And it's in quotes because they don't quite orbit, but for our model, we're going to say that they orbit, just to make things a little bit easier conceptually, that orbit the nucleus. So electrons live in shells that orbit the nucleus, and there's a very specific way that these shells are ordered. So shell number one always has 2 electrons. Always has 2 electrons. Shell number 2 always has 8 electrons. Shell number 3 always has 8 electrons. And I'll give you a guess about shell number 4. It always has 8 electrons too. Okay, so when we draw our electron shells, we always draw them in this format. So the first one has 2 electrons, the second one has 8. For carbon, since we only have 6 electrons, we're only going to be going up to the second electron shell, and we won't be filling it completely. So let's draw this out. Let's draw our nucleus again, just for fun, so we have lots of space. So we're going to say protons was 6, neutrons was also 6. We're going to draw a little circle around here to say these are all nicely contained. I'm going to draw a better circle. Nicely contained in our nucleus. There you go. Okay, so we need to fill up 6 electrons. We need 6 electrons. Exclamation point, because we're happy. So the first shell always has 2 electrons. So let's draw, I'm going to draw this in yellow. Let's draw the first shell here. The first shell, the first shell. And it always has 2 electrons. And the way that we're going to draw these electrons on is we're going to start at the top. We're going to draw our first electron. There it is. And then we're going to go to the bottom, and we're going to draw our second electron. So now there are 2 electrons in our atomic model. We have 4 left. So let's just cross out here. We've taken away 2, now we need 4 electrons. So are these 4 electrons going to fit in our second energy shell? The second energy shell always has 8 electrons, or up to 8. I'm going to say up to here, because sometimes we don't need all of them. So I'm going to draw my second energy shell. There it is, in this beautiful barf-colored yellow. And the way that we draw these on in the second shell is that we draw them on going clockwise. So we're going to start at the top, draw our electrons. There's 1. Second one is going to be a quarter of the way around, 2. Third is at the bottom, 3. And 4. So there you go. Are we done? We needed 4 electrons in the second shell. We got them. We have, let's count them out here. We have 1, 2, 3, 4, 5, 6 electrons. And we are good to go. Put a little check mark here. Yay! So that's what our Bohr-Rutherford diagram looks like. And the reason that we're drawing these and taking so much time, that's a terrible check mark. The reason that we're drawing these and taking so much time is because these are going to help us understand how different atoms bond together. Different atoms bond together. And it turns out that one of the most important things is going to be the number of electrons in the outer shell. The outer shell. Because atoms are most stable when they have a full outer electron shell. They're always most stable when they have a full outer electron shell. So this is going to be really important for us. But let's do another example first. Let's look at helium. Now, the chemical symbol for helium is He. It's called helium. Its atomic number is 2. And its atomic weight is 4. And if you look on your periodic table, you'll find all of these figures in a nice little box in the top right corner. So let's think about this for a second. The number of protons equals the atomic number equals 2. The number of electrons equals also the atomic number equals 2. And the number of neutrons equals atomic weight minus atomic number. So in this case, it's going to be 4. Atomic weight is 4. So that's right here. The atomic number minus the atomic number is 2 equals 2. Okay, so the first step was to draw our nucleus. So let's do that. We have protons and neutrons in our nucleus. So proton, P positive equals how many? 2 protons. And for neutrons, we also have 2, which we calculated above. So now that our nucleus is complete, we'll draw our little circle around it to show that these are self-contained in the nucleus. Now, how many electrons do we need? We need 2 electrons. So does anyone remember how many electrons go in the first shell? It's also 2. So we're going to have a full electron shell here at the first level. So I'll draw my electron shell looking something like this. And then I'll draw on my 2 electrons, one at the top and one at the bottom. And this is going to be my Bohr-Rutherford diagram for helium. So there's one more thing that I want to talk about, and it gets to how important the number of electrons are in the outer shell. Now, chemists love to talk about two things when it comes to Bohr-Rutherford diagrams. The first one is electron configuration. And the second is valence electrons. Now, valence electrons is simply the number of electrons in the outer shell available to bond with. So for carbon, this number was how many? Let's go up and look. So for carbon, the number in the outer shell was 1, 2, 3, 4. So the number of valence electrons for carbon is going to be equal to 4. Now for helium, there are 2 electrons in the outer shell. But since it's a full electron shell, helium doesn't want to bond with anything. It just wants to stay happily with those 2 electrons in the outer shell. And if the number of valence electrons is the electrons in the outer shell available to bond with, both of those electrons are not available to bond with. So for the number of valence electrons for helium, we're going to say it is 0. Now let's talk about electron configuration. Electron configuration is basically just a list of the electrons in each, basically a list of the electrons in each energy level. So the way that you write it is the first number is the number of electrons in the first energy shell. So let's do carbon again here. And the number of electrons in the first energy shell for carbon was 1, 2. So we're going to draw the number 2 and put a comma. The number of electrons in the second shell is the same as the number of valence electrons. So it's going to be 1, 2, 3, 4. 2, 4. Now for helium, the electron configuration, is just going to be the number 2. Because if we're listing the number of electrons in each energy level, there are only 2 electrons in the first energy level. And that means that the electron configuration is just the number 2. Now you'll notice for carbon, the second number of the electron configuration, the last number, was the same as the number of valence electrons. But for helium, it was not the same. There were 2 electrons in the outer shell for helium, but because it was full, the valence electrons is 0. So if you have an atom with a full outer shell, the number NO period of valence electrons is 0. And that's how you draw Bohr-Rutherford diagrams and use it for a little bit of analysis about the atoms that we're talking about. So let's start at the beginning. Let's do a little recap here. So first we need to find the number of protons and electrons. And we get that using the periodic table. The number of protons and electrons was equal to the atomic number. We also need the number of neutrons, and that's equal to the atomic weight less the atomic number. Now, the reason that protons and neutrons are the same is because in a neutral atom, the charge is 0. So the number of protons has to equal to the number of electrons. Step 1 was to draw the nucleus where the protons and the neutrons live. Next, we drew the electrons And the electrons live in electron shells that orbit the nucleus. We went over a little bit about how many electrons live in each shell. Shell number 1 always has 2. The rest of the shells always have 8. We went over how to fill them in. I drew a terrible check mark. We mentioned that atoms are the most stable when they have a full outer electron shell. An example of that is helium, which has 2 electrons in its first shell, which is full. We talked about what electron configuration is, which is basically just a list of the electrons in each energy shell. For carbon, that was 2-4. For helium, it was 2. And the number of valence electrons are the number of electrons in the outer shell available to bond with. So for carbon, that was 4. For helium, it was 0 because it had a full electron shell. And I said again, if you have an atom with a full outer electron shell, the number of valence electrons is 0. And this is going to help us with our determining of how things bond with each other, the number of valence electrons. It's going to become important in a little bit. But that's it for now. Thanks for watching. Oh, that's it for now. Thank you for watching. Oh my God. Let's try that again. That's it for now. Thank you for watching. And I hope this was helpful.